that this should be equal to e to the minus im psi plus 2 pi, m must be an integer, because otherwise 2 pi mi isn't equal to, because otherwise this is not equal to 1. Alright, so we now know that this has to be an integer, which is cool, but that doesn't help us solve that behemoth. Well, actually it kind of does. So let's first erase this. M has to be an integer, not just m squared. That disallows a lot of things. So this equation at first looks like it's going to kill us all. And we give up. That's it. Thank you. No, I'm just kidding. So we substitute in, let's call it, I don't know, u. That's what we usually use for a substitution, is equal to, let's go cosine theta, even though sine theta would have almost the same effect. Now, keep in mind that since sine squared theta plus cosine squared theta is equal to 1, that means that cosine theta is equal to the square root of 1 minus sine squared theta, and vice versa. I should have wrote the other one. Oops. So, what happens when you plug that in? You get minus psi 2 double prime. This is just going to be 1 minus u squared plus psi 2 prime u times the square root of 1 minus u squared minus L times L plus 1 psi 2 1 minus u squared is equal to m squared psi 2. And here's the coincidence. This is what we call the generalized Legendre equation. And it's solved by what we call the generalized Legendre polynomial. Now, that's only defined when m is an integer. But, thankfully, we prove that m has to be an integer for this to work. And this also only works when L is an integer, so just keep that one in mind. So, this is related to the standard Legendre polynomial by a factor of, actually I can't remember, but I believe it was the square root of 1 minus x squared